Hello and welcome. In this video tutorial, we're going to take a look at the workbook to AP Physics 1, Unit 7, Torque and Rotation. This video will be part 1 of a 3-part video series. Each part will look at 5 different activities within the workbook. Activity A, relationship between arc length and angle of rotation. Please remember to pause or rewind the video as needed. Read the scenario along with me, please. A coin rests on a rotating turntable. Angela collects the following data for the distance of the coin from the center, that would be the radius, the distance the coin traveled in an arc, that's the letter S, and the angle in degrees through which the coin was rotated. Part A. Remember that 2 pi radians equals 360 degrees. Use this fact to fill out the last column of the chart. Well, zoom in here. If 2 pi radians equals 360 degrees, that means pi radians equals 180 degrees. And oftentimes it's a little simpler just to use a more simplified version of it. I'm going to go ahead and do the first one with you so that you can see how you're supposed to convert them. Then I want you to pause the video and calculate the remaining radians and angles. 20 degrees, start there. We're going to multiply times the ratio of pi radians to 180 degrees. And if you multiply those, you get 20 pi over 180. Now, if you reduce that, that would reduce down to pi over 9. Now, in a math class, you would leave it as pi over 9 radians. And there will be some times in our simple harmonic motions unit where we will leave the angles and radians in terms of pi. However, in this activity, we want a decimal approximation because we are going to be graphing this data. So we can't really graph pi over 9. Well, we can, but it's a little more challenging. So go ahead and put that in your calculator, and let's figure that out. So we're going to go pi divided by 9, and we get approximately 0.35. All right, about 0.35. Go ahead and take a moment to pause pause the video and complete the calculations for trials 2 through 8, and then compare with the results that I have. Okay, for trial 2, you should have gotten 0.2524 radians, trial 3, 0.785 radians, trial 4, 1.05 radians, trial 5, 1.31 radians, Trial 6, 1.57 radians, Trial 7, 2.09 radians, and Trial 8, 6.28 radians. Part B. Which trials should Angela use if she wants to create a graph of arc length versus angles and radians? Let's see. Oh, you'll notice that trials 1 through 5, the radius is kept constant so that only the angles and only the arc length and the angles are changing, which is what it's supposed to be. You shouldn't only have a dependent and an independent variable. You shouldn't have 3 variables changing, only 2. So if you look, only trials 1 through 5 can work. And that's because the arc length and the angles are changing in 1 through 5, but after trial 5, the radius is also changing. Notice the radius is getting bigger too, and that's not going to be very useful in terms of plotting. So part C, create a graph of arc length. So arc length, we're going to graph arc length S in meters versus angle in radians. Okay, and we can scale it I scale it like every box is on the x-axis is about maybe 0.1. So that would be about 0.3, 0.6, 0.9, 1.2, 1.5. On the vertical axis, we can go not 0.1, but probably about 0.01 for every little box. So that would be about 0.05, 0.10, 0.15, 0.20, 25, 0.30, something like that. Okay, let's plot. There's only 5 values that you're going to plot. The first one is up 0.07 over 0.35. Up 0.07 over 0.35. That would put the first dot right there. The second one, the second dot we're going to plot is up 0.10, up over a little over 0.5. Up 0.10 over a little more than 0.5. About right there. The third data point we're going to plot is up 0.16 over almost 0.8. 0.16 would be about right there, and almost let's see, 0.785 is almost 0.8, so 0.8 would be about right there. So I would say the third value is approximately there. The fourth one, let's see, the fourth one we're going up 0.21 over a little after 1, up 0.21. We're going up 0.21 and over about 1. So next data point's about right there. And last one is up 0.26 over basically 1.3. 0.26 over 1.2, 1.3 is about here. There we go. Okay, so what we want to do now is we want, we're sketching it. We need to sketch a best fit line, and we want to find the slope. So let's zoom in again. Okay, so let me see. Oops. Try that again. Okay, that's a good best fit line right there. Now, if I look carefully at this, I'm looking for 2 convenient points that allow me to find the slope. I like that point there. And going up the best fit line, looking for a second one. Oh, they're hard to find. I like that point right there. So if you can find any that are closer on your best fit line, then go ahead and use them. I can't really. So I'm going to go rise all the way up to here and run all the way over to here. So I'm going from 0.04 to 0.29. So 0.29 minus 0.04 is a rise of 0.25. There's the rise. The run is going from 0.2 to, what is that, 1.4? So 1.4 minus 0.2 would be a run of 1.2. Okay, so let's figure out what the slope is. The slope is about 0.25 over 1.2. And I'm getting approximately about 0.20, 0.21. So around 0.2 meters. Okay, what is the significance of the slope of this line? Well, the equation that we're working with here that relates arc length and angle is the arc length equals the radius times the angle. This is a variable. The radius stayed constant. Theta is a variable. If I divide those two, S over theta would be rise over run equals radius, which will be your slope. The slope of the line is equal to the radius. Activity B, torque. Remember to pause or rewind the video as necessary. Read the scenario along with me, please. A long rod of length L and negligible mass supports a box of mass M. The left end of each rod is held in place by a frictionless pin about which it can freely rotate. In each case, a vertical force is holding the rods and the weights at rest. The rods are marked at half-meter intervals. Okay, so you can see where the pin is in each location. Okay, now the first thing I think we should do before we explore in part A ranking the magnitude of these vertical forces, let's get a handle on what the forces are in each case. Zoom in here. So in A, you've got the force due to gravity, and you've got the applied force up. Okay, now all of the forces have to be balanced, so that should tell you that there's also a force acting on the pin as well. And the only way to keep them balanced is, in this case, to have the force of the pin, which I'll call F sub P, directed upwards. In scenario B, you've got the applied force from the finger going up. You have the gravitational force going down, right? And in order to keep this balanced, right, you have to have the pin has to be in the same direction as whatever the outside force is. See how that works? Well, the outside force is gravity in this case, so the force of the pin is directed downwards in this case. In scenario C, you've got the force due to gravity directed down. You've got the force from the finger going up. That means the force of the pin is also directed up. In scenario D, you have the force due to gravity going down. You have the force of the finger supporting it going up. That means the force of the pin is directed up. In scenario E, we have the force due to gravity going down. We have the force of the finger going up. That means the force of the pin is up. And in letter F, we've got the force applied by the finger up. We've got the force due to gravity on the package going down. That means the force on the pin is directed down. Okay, now, something we need to know about torque in order to make this analysis work. So the variable, let's go over some possibilities here. Torque is the tendency to be able to rotate an object, and it requires a perpendicular force and a distance between the force and the point of rotation. So tau, the Greek letter tau, is this symbol here, and this stands for torque, the unit of which are Newton meters, by the way. Torque is a perpendicular force times distance, where distance, the distance right here, that's the distance of the lever arm. This is the lever arm distance. Now, the lever arm distance is not the entire distance of the rod all the time. It is the distance from the force to the pivot, okay? So each of these forces has lever distances to that pivot point. Okay, I'm going to color code them so you can see them a little clearly. So in case A, the weight is going down. This would be the lever distance for the gravity force. This, the entire length, would be the lever distance for that upward applied force by the finger. In case B, this would be the lever distance by the supporting finger. The whole bar would be the lever distance by the gravity. In case C, the lever distance of the gravitational force would be that distance there. For the supporting finger, it would be the whole length of the rod. In case D, the supporting finger right here has the lever distance of the whole bar, where the weight is only half of the bar. In case E, the lever distance is this really tiny one here because the force is really close to the pivot point, where the lever distance from the supporting force is 3 units long. In the last one, the supporting force has a short lever distance of 1 unit, and the gravitational force has a lever distance of 2 units. So it's important to know what the lever distance means and how to interpret it in a picture. Okay. All right. Now, how do we go about ranking these things? Now, since the bars, since the rods are being supported and they're not rotating, they are in what is called rotational equilibrium. Rotational equilibrium means the torques are balanced. Now, what does that mean? Let's take a closer look at letter A. Oops, that's too big. That represents the bar. Okay. Now, the weight, the gravitational force, is providing a downward force. And if the pivot is on the left end, the gravitational force would cause the bar to want to rotate clockwise. So the gravitational force causes a clockwise torque. The finger, on the other hand, is pushing upward on the complete right end of the board. So that would cause a counterclockwise torque. So you have 2 torques here. This causes a clockwise torque. This causes a counterclockwise torque. And it's good to go around each one. Go ahead and pause the video for a moment. Figure out which force, because there's only 2 forces here. We cannot count the force on the pin as being a force that contribute to a torque, because remember, torque is perpendicular force times the distance of the lever arm. The distance of the lever arm at the point of rotation is 0. Therefore, there is no torque applied at the point of rotation. So I am not going to worry about that the torque due to that force for any. The force exists, but it does not create a torque. So I'm not going to worry about that. So you only have 2 forces to worry about in each scenario. So I want you to pause the video for a moment. Try and figure out between the applied force by the finger, the supporting force by the finger, and the force due to gravity. Figure out which force is a clockwise and which one is a counterclockwise. Go ahead and pause the video now. Okay, you should have been able to come up with something like this. The supporting force in case B provides a counterclockwise torque. The force due to gravity would cause a clockwise torque. In case C, the force of gravity causes a clockwise torque. The supporting finger causes a counterclockwise torque. In D, the supporting finger causes a counterclockwise torque. Gravity causes a clockwise torque. Again, gravity causes a clockwise torque in E, counterclockwise torque by the supporting finger. And lastly, the supporting finger makes a counterclockwise torque, and gravity causes a clockwise torque. Now, how is this useful? Well, if counterclockwise torques equal clockwise torques, meaning they're balanced, what that tells you is the force times distance, because that's what torque is, force times distance, right? The force times distance going clockwise equals the force times distance going counterclockwise. Meaning the force times distance equals force times distance. I'm going to call F the force from the finger. So the force from the finger times, I'll say X. I'm going to call X the distance from the supporting finger to the pivot point in each case. Okay, so you can see what X is in each case. So F times X is the torque due to the supporting finger, and that's always going to be balancing the torque done by the weight, which is mass times G, that's the weight, times, we'll just say D. D is the measure of the distance of the right. Okay. All right. Now, in part A, you're supposed to rank the horizontal forces. So let's go ahead and solve for F. And F is equal to mg d over x. So to rank them, now the weight is the same. This is a constant. What's going to change in each case is the ratio of the distances. So let's figure out the ratio of the distances in each case, and that's going to tell you essentially how big the force is going to be. All right. So in case A, we'll do this over to the side right here. So case A, B, C, D. Well, let's do it one at a time. So in case A, the ratio, we're talking about the ratio of the distance from the weight to the distance of the applied force. Okay, so in case A, the weight is 1 unit over, and every unit is half a meter. So in case A, we're looking at mg times a half a meter over the full length of the rod, which looks to be 2 meters. Okay, so in case A, we have a half divided by 2, so we're looking at about 0.25. Case B, you've got the weight times the ratio in case B. Let's see, remember the ratio of the weight. Now in case B, the weight is all the way at the end, so that's the full 2 meters, and the supporting force is only 1 meter, so that would be 2. Case C, we have the full weight of the package times the ratio of, let's see, 1.5 over 2. 1.5 over 2 is about 0.75. Case D, we have, let's see, the mass is 1 unit over, two blocks would be 1 unit over, and the supporting force is 2 units over, so that would be 0.5. Case E, we have our weight with a ratio of 0.5 over 1.5. 0.5 over 1.5 is about 0.33. And then letter F, let's see, the weight is at 1 unit over, the supporting force is a half a meter over, which would be 2. So looking at here, B and F are the largest. So we'll say B is equal to F as largest. The second largest would be, looks like C, 0.75. Then it would be D, 0.50. Then it would be E, 0.33. And then finally it would be A, which is 0.25. Okay. Okay, explain your ranking. Since the system is at rest, we know the sum of all three forces on each system and the sum of all three torques on each system is also 0. In other words, forces and torques are balanced. Torque is caused by the force at the pivot point is 0 because torque cannot act at the point of rotation, right? The lever arm distance is 0, and so 0 times any force is 0 torque. This means the torque from the weight must equal the torque from the force supporting by the finger. In each case, the torque due to the supporting force, which is force times distance x, is equal to the torque caused by the weight of the package, which is mg times the distance of the package, where x is the distance from the finger to the pivot and d is the distance from the box to the pivot. The closer the box is to the pivot, the less torque is required to hold it up. On the diagram above, sketch the forces. We already did that. In part C, in which cases is the force from the pin up, down, or 0 justify your answers? Well, in no cases is the force 0. There's always a force acting on the pin. But in cases B and F, if you go back and look, B and F, the force of the pin is downward to balance out the downward, outward force of whatever's on the outside, the weight of the package. A, C, D, and E, the force of the pin was all upwards. So we can see that directly from the picture. Part D. In a short paragraph with reference to the picture above, why is it easier to hang a shopping bag from the crook of your elbow than to carry it suspended from your hand with your arm at a 90-degree angle? Assuming the elbow is the pivot point, when someone is holding the bag with their hand, there is a torque around the pivot equal to the magnitude of the weight of the bag times the length of the forearm. When the grocery bag is held at the elbow, no torque is created there because there is not a perpendicular distance between the pivot point, which is your elbow, and the force of gravity of the bag. Activity C, rotational energy. Well, when we used conservation of energy principles before, we were typically converting between gravitational potential energy and kinetic energy. Now, the kinetic energy we were used to using was translational kinetic energy, which is 1/2 mv squared. So let me just comment on that really quick. If you have an object that's rolling, and it's moved to that spot over there, the center of mass will have moved that particular distance d. That center of mass corresponds to a straight line translational kinetic energy. The rotation, on the other hand, corresponds to a rotational kinetic energy. So this is a case where you have both. The total kinetic energy would be translational kinetic energy, which is 1/2 mv squared, plus rotational kinetic energy, which is 1/2 I omega squared. The scenario is as follows. A solid sphere is initially at rest at the top of a tall, rough hill. It rolls down the hill and up the next one. Okay, so Angela, Blake, and Carlos create energy bar graphs for the sphere Earth system for the time between when it was released at point A and when it reaches point B at the bottom. Explain why it is either correct or incorrect. Okay, so let's start with Angela. Angela says we start, in fact, all three students say we start with gravitational potential energy. Well, that's true. We start with mgh. However, you don't just have 1/2 mv squared at the bottom because the sphere is going downhill. It's translating its motion, but it's also rotating at the same time. So you have 1/2 I omega squared of rotational kinetic energy as well. You have both of them. Angeles does not support that. Angela says that all of our gravitational potential energy converts into rotational kinetic energy only. That would mean that the sphere is just simply spinning in place at the top and not moving forward. That's not true. Blake states that the gravitational potential energy becomes completely translational kinetic energy. Well, that's not true either. That would be if the sphere were gliding on a slick hill and not rolling. So like, for instance, when you roll a bowling ball down a bowling lane, for the first 5 to 6 feet, it doesn't rotate. It just glides along the waxed floor. And then all of a sudden it catches hold and the bowling ball begins to rotate the rest of the way down the alley. Well, Blake is suggesting that gravitational potential energy becomes the translational kinetic energy of a gliding sphere. It's not gliding, it's rolling. Carlos, on the other hand, is suggesting that the gravitational potential energy is partly translational, partly rotational. It is more translational than rotational, but there's still the two of those energies have to add up to the potential energy you started with. Okay, let's summarize these down below. Angela's graph is incorrect because it shows all of the initial gravitational potential energy has been turned into rotational kinetic energy. An object that has only rotational kinetic energy is spinning and not moving with forward motion. This does not correctly represent the motion of the sphere at point B, as the sphere is clearly moving with forward motion past point B. Blake's graph is also incorrect because it shows that the initial gravitational potential energy has been turned into translational kinetic energy. An object that has only translational kinetic energy has no rotation. This does not correctly represent the motion of the sphere at point B, as the sphere is clearly rolling as it is moving with forward motion. Carlos' graph is correct and shows the sphere will have both rotational and translational kinetic energy at point B. The 2.5 ratio, if you look, you can see the rotational kinetic energy is 2/5 of the translational kinetic energy. The 2.5 ratio, the translational kinetic energy being 2.5 times greater, comes from the rotational inertia of it's a typo there, the sphere, which is 2/5 mr squared. Part B. How would each bar chart in Part A be drawn if Earth were not part of the system? Well, if Earth were not part of the system, you would not have gravitational potential energy, but instead you'd have the work done by the gravitational force. This would be the case because the force would be outside the system. Part C. The sphere continues to roll along the track without slipping at point C. It leaves the track at that point. At the sphere's highest point, it will be above, below, or at the same height as point A. Let's re-reference the picture again. So you got the A, B, C. So A's up here, B's down here, whoops. C is where it leaves the track. Okay, so the ball is going to roll down, 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 and it's going to leave the track. And it's going to leave the track at an angle like this. And it's going to end up becoming a projectile. Now recall that projectiles have horizontal velocities, which remain constant, and vertical velocities, which are slowing down when you get to the top. No vertical velocity at the top, only horizontal velocity, and they're getting bigger going down in the negative direction on that side. Okay, so we have a projectile here. So here's what's going on with the sphere, though. The sphere, as it rolls off the track, it's going to continue to roll. Think about that. Why would the sphere stop rolling in midair unless a torque were applied on it to cause it to stop rolling? Well, there is no torque acting on the ball when it flies through the air, so it will continue to roll. So if it continues to roll, it's still going to maintain rotational kinetic energy flying through the air. What that means is it will not have the same potential energy to get back to the highest point. So it's going to be somewhere below point A when it's flying through the air. Let's go ahead and summarize this. When the sphere leaves the track, it will have a vertical, that should say, vertical, horizontal, it has vertical and horizontal components of velocity. The vertical component will be changing because the sphere will be accelerating vertically due to gravity. The horizontal velocity will not change. Therefore, the sphere reaches its maximum speed, it will have horizontal speed and thus some kinetic energy. Because it will not be able to travel as high, because some of the sphere's kinetic energy was turned into a little bit of gravitational potential energy, but some of the initial potential energy was converted into rotational energy, meaning we start with gravitational potential energy. At point B and point C, you have translational and rotational all the way. Well, that's kind of true at the highest point here. At the highest point, you've gained a little bit of gravitational potential energy, translational kinetic energy, and rotational kinetic energy. It's still going to rotate. So once the sphere leaves the surface, it will continue to rotate, so this energy will not be converted into as much gravitational potential energy. Part D. The sphere is taken to an identical shaped track with negligible friction and released at point A. The sphere's maximum height after leaving the track is greater, less than, or the same as the height that it reached on the rough track. In this case, it's going to be greater. On the smooth track, the sphere will not roll. Instead, it will slide, meaning that it will not have any rotational kinetic energy, but only translational kinetic energy. This means that the speed with it leaves the track at point C will be greater than when it was rolling. Therefore, it will have a larger vertical component, and thus will travel higher. Activity D, forces versus torques. Again, please remember to pause or rewind the video as necessary. Read the scenario along with me, please. A box of mass M is tied to a rope that is wrapped around a pulley. The pulley is initially rotating clockwise and is pulling the box up. The box slows down, stops instantaneously, and then moves back downward. Part A. Number 1. The dot below left represents the box. Draw a free body diagram showing and labeling the forces, not components, exerted on the box initially. Draw the relative lengths of all vectors to reflect the relative magnitudes of the forces. Each force must be represented by a distinct arrow starting on and pointing away from the dot. Well, you basically have the force from the hand that's, pushing the box. So somebody's hand pushes this box upwards and it gets the whole pulley system to start rotating counterclockwise. The box is going to get to a highest point, it's going to stop, and then it's going to come back down again, at which point the pulley will now be rotating clockwise. Okay. That means I'm going to call this, I have the force due to gravity acting downwards, and I have, I'm going to call it the normal force. The normal force is the force from the hand, the surface being the hand, acting upwards. Why is the gravity bigger than the normal force. Well, remember what's going on. When you're going upwards, but you're slowing down going upwards, which means although your velocity might be up, your acceleration and thus your net force have to be going down. If your net force is going down, gravity has to be the larger force. Part 2. On the diagram to the right, draw and label the components, forces, not components, on that are exerted on the pulley as it initially rotates. Clearly indicate at which point on the wheel the force is exerted. Draw each force as a distinct arrow starting on and pointing away from the point at which the force is exerted. Okay, well, what you have in this situation is you have the weight of the pulley going down. However, the pulley is not accelerating up nor down. There's no acceleration of the pulley. That means the forces, the vertical forces on the pulley have to be balanced. So you also have tension acting on the side of the pulley, acting on the rope going downward. And the tension and the gravity have to add up and balance the force from the bracket at the point of rotation, which we'll call, again, the normal force. This force plus this force have to balance that force. Part B, what force is responsible for the net torque on the pulley? The force of tension is responsible for the net torque on the pulley. Even though there are three forces, gravity, the force from the pivot, which we call the normal force, and the force from tension, the pivot force here and the gravitational force are acting at the point of rotation. So you'll remember that torque is equal to a perpendicular force times the distance of the lever arm. Well, the distance of the lever arm is the radius of the pulley. These two forces are applied at the point of rotation. Therefore, the distance is 0 and the torque is 0. There is no torque. So let's make a note of that. No torque caused by this, no torque caused by this. Part C. Sketch a graph of angular velocity as a function of time from the instant the weight comes back down. So when it comes back down, we're taking counterclockwise as positive. So the instant it comes back down, right here, it's okay, so I think I read that incorrectly. So this is the final point. So first, we're going to take it from the initial instant, in which case the mass is going up. If the velocity is going up, that means we are rotating counterclockwise, which is taken as positive, where you have initial velocity, therefore you have an initial omega. So I'm going to start with some initial omega value. And what's going to happen is that omega value is going to decrease because the spin is going to stop, and then it's going to start to come back down, which would be clockwise rotation or negative omega. And that would produce a graph that looks a lot like that. Now, since alpha is the slope of omega, that's clearly a negative slope, that's negative alpha. So I can sketch a constant negative alpha for the exact same time interval. Activity E, rotation. Please read the scenario along with me. A meter stick is set on the edge of the table so that all but a negligible bit of its length is off the edge of the table as shown. The meter stick is released from rest horizontally. The meter stick's mass is m and its length is L. The rotational inertia of the meter stick about this left endpoint, or about either endpoint, is 1/3 ml squared. Part A. Sketch a force diagram for the meter stick just after it has been released, meaning that it is still horizontal, but there are no longer any supporting forces supporting the right end of the meter stick. Remember, a force diagram differs from a free body diagram in that the forces are drawn from the point of application rather than just the center of mass. So just the moment after it is released, you've got the force due to the gravity at the center of the meter stick and the normal force due to the table over here. And when you release this force here, when you release this force horizontally out this way, there's no longer any force there. So our force diagram would look like this. Part B. Identify the point on the meter stick around where the meter stick is pivoting. Mark this point with an X. Okay, well, we are pivoting here. I'll mark it with a blue X so you can see it easier. We're pivoting around that point right there. Is there more than one choice for the pivot? What are your implications? Okay. You can actually choose any point for your pivot. Remember now, torque is equal to a perpendicular force times distance. So wherever your pivot is, torque equals 0 at the pivot. Now that is a strategic choice. So again, you can choose any point, but you would need to either know or calculate a new rotational inertia for the rod at that point. So that's number one. So having a rotational inertia of 1/3 ml squared means we need to pivot either around that point or that point. Since there are no forces acting at that point, it would make sense to use that. You would also need to know the magnitude of the normal force at the end of the meter stick. Since we do not know the magnitude of the normal force, it makes sense to choose that as our pivot. So if you choose the point of application of the forces as the pivot, it makes sense. It makes the solution much simpler. Then at that point it will be 0. Part C. Determine the net torque about the meter stick's left end instantaneously after being released. Okay, so net torque does equal I alpha, but let's figure out what the net torque is. Now, this does not contribute to any torque at all because it's at the point of rotation. So the only torque contributing to the net torque is right here. This is the only torque acting on this. So the net torque is due to the weight, which is the force due to gravity, which is mg. But it's acting at a distance of half. This is the full length of the meter stick. It's acting at half the length, L. So we could just say mgl over 2. The net torque on the stick includes both the torque from the force of gravity and the torque due to the normal force. But since the normal force is at the pivot point, the distance between the normal force and the pivot point is 0. That means the torque from the normal force is actually 0. So the net torque only is contributing from the gravity acting on the center of the stick. Part D. Starting with Newton's second law of motion in rotational form, derive an expression for the initial angular acceleration of the meter stick in terms of ml and physical constants. What we will do is we will derive it and then we will describe it. So we'll go left and then we'll go right. So first, net torque equals I alpha. The net torque on the meter stick is equal to the rotational inertia times its angular acceleration. Okay. Well, something to consider about the net torque. The net torque was found to be mgl over 2. In other words, the torque from the force of gravity is the only net torque acting on the stick. We're going to set them equal to each other now. And mgl over 2 equals I alpha. Okay, so since the net torque is equal to I alpha, we set them equal to each other. Now what we're going to do is we're going to substitute for I. So we have mgl over 2 equals 1/3 ml squared times alpha. Barely fit that alpha in there. There we go. We're substituting the rotational inertia of not a beer stick, a meter stick, about the end is 1/3 ml squared. Okay, now masses cancel, 1 factor of L cancels. We would multiply by 3, so we get 3 halves G over L equals alpha. Part E, derive an expression for the linear acceleration of the far end of the meter stick, not on the table, in terms of G. What are the consequences of your answer? Explain in terms of what would happen to a penny placed on the end of the rod before it was released. Okay, so let's start with this right here. Alpha was 3G over 2L. We know that A is equal to R alpha, and R, that it's rotating, is the length. So alpha is equal to A over L. Set those equal to each other, and 3G over 2L is equal to A over L. L's cancel. A is equal to 3G over 2. What does that mean? It means the acceleration at the far end is greater than G. So if I were to just drop the meter stick and drop a penny, it's going to fall at a rate of G. But the right end of the meter stick is actually falling faster than G. So what that means is if you have a penny placed on the end of the meter stick, like this, as it begins to rotate some split second later, the end of the rod will have accelerated greater than the penny. The penny's falling at G, the end of the rod is falling at 3 halves G, which is 1.5 times G. Therefore, if you looked at it in slow motion, the right end of the rod actually rotates a little bit greater acceleration than a falling penny. Let's go ahead and summarize this. The acceleration at the right end of the meter stick is greater than the acceleration due to gravity. 3 halves G is greater than G, meaning that if a penny were placed on the right end of the meter stick before it was released, the penny would fall accelerating at G, while the end of the meter stick will accelerate at 3 halves G. So the meter stick would appear to leave the penny behind while it accelerates down and away from the penny.